Hi everyone. In this lecture we're going to talk about paging. We're going to have a brief introduction to paging and talk about some of the calculations that you can do having to do with paging, and you'll see some on your homework. So last time we talked about contiguous memory allocation, and this is where we have a set of processes and we have our memory, and we can start putting our processes into memory where the process has to be completely all contiguous together, so you can't break up the process and put it in different places. I don't know, and so we add process 2, ... So this was contiguous memory allocation. So the problem with contiguous memory allocation that we saw was fragmentation. And we saw two different types of fragmentation. We saw internal fragmentation, where the assigned space was not completely used up by the process. So this was the process and this is what it was using, but there was this empty space where it wasn't being used. So this was internal fragmentation. We also talked about external fragmentation, where the assigned space is here and here. So these are assigned to some sort of processes. And then we have these holes in between. So these fragments are the holes. And now if we have a process come in that needs 50 kilobytes of space, we have it. We have 40 here, we have 10 here, but we don't have it in contiguous spots. So therefore we can't let this process run because we don't have it in contiguous locations. So this was the main problem. One possible solution is called paging. So the goals of this lecture is to talk about what is paging, how might we implement it, and finally, how does it solve the problems that we faced using contiguous memory allocation. So first off, what is paging? So the idea behind paging is that we take our virtual memory and we divide it into chunks which are called pages. So each one of these is a page, and we take our physical memory, or our RAM, and we divide it also into frames. So each one of these is a frame. Now, usually page size and frame size, so page size is going to be equal always to frame size. And this will make sense when we talk more. The idea here is that your program and all of your memory can be split into these different pages, and now you can, so say if both of these pages belong to process 1, now we can store each page into potentially different spots in memory. So now we have this non-contiguous memory allocation. And the idea here is that we'll get rid of those holes and all that fragmentation that we saw from before. So this is the general idea. So in general, frame size is usually a power of 2, and it can be between 512 bytes to 16 megabytes. And why? So you'll see this. So this makes the translation of the logical address to the page number and offset easier. And so we'll talk more about that in the next. So how do you implement paging? So now what you have is you have each one of the addresses. So say we're looking at a 64-bit computer. So each one of the addresses are going to be 64 bits. These are going to be partitioned into two parts. We have a P and a D for pages, and these are pages in virtual addresses or logical addresses. Those are the same. And so it's going to be partitioned into a page number and a page offset. And so what the page number is going to tell us is it's going to allow us to index into what is called a page table. So this is the page table. Now the page table is going to hold the ID of the frame number that's going to let us get into the right frame in memory. So this P here is going to tell us the page number, so it's going to let us index into the correct page in the table. And that page in the table is going to hold the frame number, so it's going to allow us to look for the frame number. What this offset is, so I'll give a more concrete example in the next few slides, but what this offset is that not only do you maybe have to index into the page table, you also will need to index into an actual page itself. So imagine this is our virtual space here, and so this goes on forever, but or not forever, but this is one page. Within the page, this could have multiple spots, and so this offset is going to tell you where in this page you're sitting. And so this page offset is going to be the same as the physical address offset, so this will also allow you to index into where you need to be in the frame. So if this is the frame, we got some positions in here, and so D is going to let us know where we need to offset. So this was for the physical address. There's a similar one for the, this was for the logical address. There's a similar one for the physical address. But instead now we're going to use F to denote the frame number, and D is the same offset that we saw before. So here, the frame number is the number now that instead of indexing from the logical address to the page table, it lets us go from the page table into the correct frame in physical memory. And the offset is going to tell us how far down in that frame we need to go until we find the spot in memory that we are looking for. So here's one really simple example. And in this example, we have our logical memory, and we're just splitting it into these, block page numbers. We have our page table that tells us our translation from the logical memory into the physical memory. So for instance, if we wanted to find if our CPU generates a logical address of something that's in page 2, we want to be able to take the logical address, look it up into the page table. So this is in the second page, so we would come here, and this would tell us that our page 2, everything in page 2, all the addresses that belong here, are in the page or in the frame 3 of the physical memory. So we would go here, and that is exactly where it is sitting. Okay, so that's an easy example. A more complicated example is as follows. So now in our logical memory, we don't just have those blocks of 1, 1, 2, well, let's index from 0 because this example assumes that. So we'll say 0, 1, 2, 3. So it also lists out the actual, some entries within a frame. Okay? So now, if our CPU generates the address of A, so A is here. Now we need to figure out where A is sitting here. To do that, we are going to find the P and the D for A. So for P, it is sitting in the 0th page. So P is 0. And for D, it doesn't have an offset, right? So A is the very first memory address within that page. So it has no offset, so its offset is 0. So what we can do now is we can, let me erase this. So we can say, okay, so A is in the 0th frame, so 0th page, so we'll come here and we find that it is in frame 5. So if we 2, 3, 4, 5, 6, 7, so here, and we see that it is at offset of 0, so we'll point to the very first one. Okay, so notice one thing, but we'll talk about it I think in the next slide. Yes, is that this is of course numbered continuously, it's not numbered 0, 1, 2, 3, 4, 5. So there will be an extra step of address translation, but we'll get to that in a second. Let's do one more example here. So, did not want to do that. Let's erase this part. Okay, so we did it for A. So now let's do it for N. So for N, what's P? Well, so P is going to be the page number, so 0, 1, 2, 3. N is here, so N is in page number 3. So we will index into index 3 in our page table. We'll find that this is sitting in frame 2, so we'll come to 2. And now we need to figure out what our offset is. So we came to frame 2, we're here at frame 2. We need to figure out how far down in frame 2 we need to go to get where N is sitting. So we come back over here to our page, and we see that N has an offset of 1. Sorry, what did I say here? 3? So N has an offset of 1, right? So M has an offset of 0, N has an offset of 1. So now we know that we need to go down to index 1 inside of the second frame. All right, so this is, we're getting a little bit more complete of an example. Of course, you know, we're going to deal with really ugly memory addresses, but in general, this is a good example. So now, so we have the same image here, same positions of everything. So now we assume that the CPU produces a virtual address of 11. Okay, so it's produced 11. Now we need to see how will this be translated into a physical address. So this is 11 here. We want to know what number 0 through 31. Which one of these is equivalent to 11? Okay, so again, how we do that, just from before, we see that the entry 11 is in the second page, so we're going to index into the second page of our page table. So here, we'll write some things down. So our page number is equal to 2. Our frame number now we see our frame number. Our frame number is 1, so we'll say frame number equals 1. And our offset is, so our offset is 0, 1, 2, 3. So offset equals 3. All right, so we know that this is how the translation is going to happen. We're going to go, we're going to get to frame 1, and we're going to go down 3 to get to L, which is what is at address 11. Okay, but how, so this is what 8 is 4, 5, 6, 7. So this is address spot 7. How would we actually get to that number with the numbers that we have here? So the calculation will be like this. It will say, so the frame number times the frame size plus the offset, right? So the frame number, so we get here, this would be the frame number. I'm sorry. The frame number times the frame size would get us here, right? So the frame number is 1 times the frame size, which is 4, plus how many more we need to go, which is our offset, plus 3. And that would get us to 7. Okay, I hope that makes sense. Moving on. So let's ask some more real-world examples. All right, so imagine we have a 64-bit machine. So all of our addresses are going to be 64 bits. And we have 16 terabytes of RAM in that machine, and we're using a 4 kilobyte page size. So I can ask you several questions about this. I'll ask you a few. So the first question is, how many memory frames does this machine have? Okay, so we have 16 terabytes of RAM, and we want to divide those up into 4 kilobyte. No, we have a page size here. Oh no, what's our frame size? Okay, well, so before, like we said, so frame size is going to be equal to page size. So this is equal to frame size. Okay, so we're going to take the total RAM and we're going to divide it by the frame size. Okay, so total RAM. Total RAM is 16 terabytes. You want to work everything in powers of 2. So 1 terabyte is equal to 2 to the 40th. Okay, and we have 16 of those terabytes. So times 16. But we know that 16 is 2 to the 4. So we have this, and when you multiply, you add the exponents, little review. And so we get that our total RAM is 244, or 2 to the 44th. And this is in bytes. Okay, so now we want to divide this by the frame size. Okay, so what's the frame size? Frame size is 4 kilobytes. 1 kilobyte is equal to 2 to the 10th. And we have 4 of those, so times 4. This would be 2 times 2 to the 2nd. 2 to the 10th, which equals 2 to the 12th. So we'll divide 2 to the 44th divided by 2 to the 12th. And when you divide, you subtract the exponents. So you're going to get 2 to the 32nd. All right, so this is the total number of frames that this machine has. So if we divide all of our memory up into frames, this is the amount of frames that we have. Okay, so the next question I'm going to ask is, how many bits are needed for displacement into a page? So same system, same amount of RAM, same page size. So how many bits do we need for a displacement within a page? So remember now, we have the yellow, I haven't used yellow yet. So we have this as our address. We have the page number, which is going to index us into the page table. And we have the offset. So what I'm asking here is the offset. How many bits are needed in this portion of the address to encompass all of the number of bits that could possibly be in a page? So we already kind of know this, and it's a pretty straightforward calculation. So basically you take the page size, you convert it to its 2 to the n representation. So 4 kilobytes again, 1 KB is equal to 2 to the 10th, and we have 4 of those, so 2 to the 2nd. So this is going to be 2 to the 12th. So if you have it in this form, then you immediately know that 4 kilobytes of space can be addressed using 12 bits. So 12 bits. Okay? All right, so the next question I'll ask is, so assume that it takes 36 bits to index into the page table. So that's that P here. How large can our virtual memory be in terms of bytes? All right, so the first question here to ask is, how many entries can we have in the page table? If we have 36 bits to address into this page table, then that means that we can have 2 to the 36 entries. Okay, so this is entries though. This is not in bytes, so we can have 2 to the 36 entries. So now we need to figure out how much space is that going to take up. So an entry is equivalent to a page. So, and we know that our pages are 4 kilobytes. So all we do is we say 2 to 36 times the page size, which is 2 to the 12th. We've already done that calculation, so I'll just skip. And we get that 2 to the 48, barring any dumb math errors. No. Nice. Okay, so we get that this can be 2 to the 48 bytes. All right? All right, question 4. What is the size of the page table in terms of 4 kilobyte pages? Okay, so now I'm sorry. So oh, darn. I jumped ahead of myself here. Let's see if I can. All right. I can't figure out how to delete what I've already said. So let's go back to this. The answer that we have is correct, but I have written this a little bit misleadingly. Okay, so we'll backtrack here. All right. So you have 2 to the 36. I'm sorry. You have 2 to the 36 entries here in your page table. And the question was, how big can the virtual memory be? So I was doing the page table calculation, which is actually what's on the next slide, and this is not the amount of space in the page table. This is the amount of space in the virtual memory, which is here. So here, the connecting factor is if I can, if there's 2 to the 36 possible entries in my page table, that means I can have 2 to the 36 pages here. Okay, because each one of my pages can index in one-to-one to the entries into my page table. So that's the connecting factor. And it's the same calculation here. So if we can if this is the number of pages that we have now, so we'll get 2 to the 48 bytes. Okay, so now we want to know what the size of the page table is going to be, and we want it in terms of pages. All right, so here we already know that the page table here has 2 to the 36 entries. And so each entry is an address. So each entry is going to have an address to the frame table, right? So it's going to have the frame number and then store the offset. Really, it just needs the frame number, but so it's going to have that. So each one of the entries here, the size, is going to be equal to whatever size this is, and we know that this is 64 bits, right? We have a 64-bit machine. So we have 2 to the 36 entries times the size of each entry. So we want to find the total size. So total size in bytes of the PT, the page table. So 2 to 36 times 64 bits, which is equal to 2 to the 36 times 8 bytes, which is equal to 2 to the 36 times 2 to the 3, which is equal to 2 to the 39 bytes. So this is how big that the page table is, okay? So, but now I want it in terms of 4 kilobyte bytes, or pages. So straightforward here. we have this is our size divided by 2 to the 12th, that's our 4 kilobytes, and this is going to equal 2 to the 27. Okay. So this, I have 202 to the 27 pages, or 4 kilobyte pages in my page table. All right. So the last question we want to ask is, how does this solve the problems we face with contiguous memory allocation? So the first thing is that we no longer have to do contiguous memory allocation, and this is going to afford us that we no longer have to worry about internal or external fragmentation. So internal fragmentation is, out of the way because we just have these frames and these pages, and the size of the frames is equivalent to the size of the pages. So you're never going to have any internal fragmentation where you're going to have wasted space within a frame or a page. And external fragmentation, so since we're working in these known units of space, we're not going to have that either. At the most, we're going to have something come in and it's just going to need a frame. Potentially it could need too many frames that we have, so we could potentially run into some external fragmentation. So I'll put potential. Probably butchered the spelling of that, but that's all right. So this is potential, but it's less likely than before, and it happens a lot less frequently. So what are the drawbacks? So in this this paging example, we've used a single page table, and the problem with this is that these page tables can be huge. So if we look at our example from before, so from question 4, our page table was 239 bytes. So if you do the math and you convert this back out to gigabytes, then, so 2 to the 30 is 1 gigabyte times 2 to the 9, that'll be 1 gigabyte times 512. This is 512 gigabytes. And so remember that these pages, they have to sit somewhere, and they're going to sit in memory themselves. And that's a lot of space to take up for just your page table. So this is not scalable in the single page table method. So the solution to this is multi-level paging. And the general idea here is that you have your virtual space, and so that's going to index into an outer page table, which then is going to index into a series of inner page tables. And the total space that's used by all of these together, so these are inner, is going to be the same as this. So the question is then, where do we get, the reduced in space requirement? We do, it's kind of clever, and I'll tell you that in the next lecture. So next time we're going to talk about multi-level paging, and the time after that we'll talk about speeding things up with a translation look-aside buffer. So let me know if you have any questions, and thank you.